Today, we're going to talk about the fundamental theorem of calculus. We're going to start with a function f of t, the curve shown here. And we're going to look at taking the area under f of t between the values of a and b. Both of these values are on the t-axis. So we can see that the area under this curve does not appear as any regular geometric shape, like a circle or square or a triangle. So we're going to need to be creative about how we're going to get the area. We're going to estimate the area under the curve. Well, if we draw these 5 rectangles under f of t, we see that the area of those rectangles can give us a pretty good estimate of the area under f of t. And I've chosen to use the left side of each rectangle, okay, to align with the function f of t. So let's build an expression that gives us the area, using the function f of t and the intervals on the t-axis that will give me the width of my rectangles. So the first term, representing the first rectangle right here, is f of a times delta t. The second rectangle would have a height that is f of a plus delta t. So this is a new t value that is delta t away from a. So it's right here. And that is the height that I've chosen for my rectangle. And that is multiplied by the width of the rectangle, which is also delta t. For simplicity, we've decided to let all of the widths be the same. The third rectangle would have a height that is 2 delta t's away from a. So we're going to write that value of the function as f evaluated at a plus 2 delta t's. Okay. This is simply the t value where we are evaluating the height of this third rectangle. This is the t value right there. And this is the height, f, right? And I'm going to write it as f of t3, just so that I can not clutter that axis up too much. But we know that t3 right here is equal to a plus 2 of the interval widths. Now we would continue, let's multiply again by the width of delta t. And remember that all of these terms are the areas of the rectangles. And we continue to write the expressions for the last 2 rectangles. And the sum of all of these terms would give me an approximation of the area between a and b under the curve f of t. Now we can write this using a summation symbol. Okay. This is a summation symbol, and we could use an index I to identify each of the terms from 1 to 5. There are 5 terms here. There are 5 rectangles. And the individual terms could be written in a general way using a formula saying that we would start at some x value, some t value, which we're going to call t sub I. Let's clear that up. T sub I. And t sub I would just be a label that we'd use to identify each of these points between A and B. So T sub 1 would be A. T sub 2 would be this A plus delta T, and so on. T sub 5 would be the A plus 4 delta T's. Okay? And we would multiply each of these heights by delta T. Now, delta T can be precisely identified if you tell me the number of rectangles that you want, which would be 5, and the width that we have, which would be B minus A. So B minus A divided by 5 would tell me the width that I need for each rectangle. So this expression here can also be rewritten with a general n, which is the number of rectangles, the function, which is giving me the height of each rectangle, and the width, B minus A, divided by the number of intervals. Okay. Now, how can we get this area more accurate? We know that there's error associated with our approach because we can see all the white space, right, that has been left out. And in some cases, there's some overshoot on the right side here. So to get this more accurate, we would want to create smaller rectangles so that the amount of error would be reduced. The amount of overshoot or underestimation would be reduced. If I let n go to infinity, the delta t then goes to 0. And what we have in this expression is what we call an integral. And we will take the f value, which is this function here that's giving me the heights of the rectangles, and we'll simply write t instead of t sub I, since between A and B we would have essentially sampled every single t value, if you can imagine an infinite series of terms. And the delta t here, the interval of each rectangle, has now gone to 0, but we're going to use what we call a differential dt to represent this infinitesimally small rectangle width. Now, this summation here has a special name. It has been called a Riemann sum because of the fact that it uses rectangles. It is the summation of rectangles underneath a curve. And the curve becomes the heights of each rectangle. The height is sampled somewhere inside each interval. So the Riemann sum here, when taken to the limit, when the n, or the number of rectangles, is allowed to go to infinity, the Riemann sum becomes the integral. This is the definition of the integral. Now, the integral symbol is very efficient in that we now have room to specify the interval width, the total interval width of B to A. These are called the limits, the upper limit and the lower limit. The upper and lower limit of the integral should not be confused with the limit that we've been taking since the beginning of our calculus course. That limit means that you're looking to take a value to a certain point and get as close to that point as possible. But this a to b is simply talking about the boundaries of the function f, where we're taking our area. So we have lower and upper limits. Now that we've made this relationship, we're going to talk about some very special properties of the integral. This will lead us to our fundamental theorem of calculus. So right now we've associated this integral with the area under the f of t. If I allow the b to slide so that it is not a fixed point, but it is a variable, we can look at this and imagine a small change in the x variable. So we're going to allow the b value to be variable. We'll start at a again here. And we understand from what we just learned that this entire shaded region here can be represented by the integral from a to this variable x of f of t dt. Now it's important to note that the x variable is on the t-axis, but it is different than the t variables that are being specified here. The x variable represents the specific endpoint, the upper limit as we've understood it, for my area function here. But the t variables inside the integral represents all of the values that we are sampling as we add the rectangle areas. So the t and the x have different roles, different meanings. The x is a specific point on the t-axis, and this t variable represents all of the values between a and x that you use to get the area. So we have a special name for the variable that's inside the integrand, and that is called the dummy variable, because in fact, I could use any other variable I wanted to represent the spectrum of the range of values from a to x. So it is unimportant what we call this axis. It's very important, however, that we don't use the x variable, since that's already being assigned to this sliding endpoint. Now, we're going to study this picture here. I'm going to clear our screen. So let's imagine that we have a small increase in our region that ended at x, and we're going to call this incremental change here in the t value, right, h. So I'm going to study how the area changes as I change my boundary x from x to x plus h. Now, when you study how an output variable changes with respect to its input variable, you're looking at a rate of change. And if you use very small intervals, you're going to be looking at instantaneous rate of change. So let's first establish the fact that this area function here is a function of x, right? If I know that this is, I want to draw it in the same color. If I know that this area is going to vary with the upper limit, holding everything else constant, right? A doesn't change, and you have the same formula of f of t dt, then the area only depends on this upper limit of x. So we've established a function here that depends on the input x. We're going to now study how this output variable a, changes when I move x slightly. Well, we can use our same formula here, a to the x plus h, okay, times f of t dt. Now what we're going to do is study the graph and see what would be the change in the area. Well, if I'm using my Riemann sum again, which we understand this to be, this is nothing more than an infinite sum of rectangles, then this additional interval here would add the additional rectangle that has an area of f of x. That's the height of that rectangle on the left side, times the width of h. So I'm going to write a of x plus h as the original a of x, that's the area to the left of the h, plus this small rectangle we just identified, f of x times the interval h. Now, we're going to do a little bit of algebra, very simple. A of x plus h minus a of x. Okay, if we've just subtracted a of x from the right side, that shall leave us with f of x times h. No mystery there, simple algebra for us. Now, if we divide by h, we will have a very familiar expression. The right side simplifies to f of x, and the left side, as you can see, is looking like the change in an output variable divided by the change in the input variable. Now, if we let the input variable change go to 0, we'll do even better. We are going to see that we now have the formula for instantaneous rate of change, or the first derivative. Remember that h is this delta x. Now, that means, okay, and let's be very complete about this. We're going to take the limit on both sides of the equation. The limit is an operator, so it needs to be taken on both sides of the equation. Okay? So we have the limit on the left side giving us the first derivative. We see this is the limit of the difference quotient. On the right side, we can simply evaluate this as f of x, because the limit does not affect the variable x. H is the slider here, not x, so this is essentially the same as f of x. Very good. Now we can see clearly that the first derivative of my area function is in fact the integrand f of x. So let's write that out. So we have f of t dt, and we're going to take the area from a to x. Now this is called the integrand, okay, the f of t specifically. And we know that this is equal to the area up to the limit x. And we're going to take the derivative of this with respect to its input x. And we know the answer, so I'm going to write the derivative of this with respect to its input x, the answer is f of x. Whatever the expression is here, the integrand's function, you would simply use that same function and write the variable x within it. This is the first part, or the derivative part, of the fundamental theorem of calculus. And we can express this, we can show an example of this. Let's take a function, simple function of e to the 2x. Let's make it 2t dt. And we're going to let the limit go from 0 to x. This is going to be the area under the function e to the 2t. Now, if I want the derivative of this, the derivative of this is simply e to the 2x. Okay, now we're going to make another connection, which will lead us to the second part of the fundamental theorem. So, if we look at our original expression, the Riemann sum, okay, that is the area under this f of t curve, we can also consider another interpretation for these products, these rectangle areas that we have collected. Imagine that f of a is actually the derivative of another function, which I'll call capital F. So let's let capital F's derivative equal little f of t. Okay, and I can also write this as dy dt. Okay, so we can see the familiar rate of change notation, and I would call the capital F my y value. So it's important that we get very comfortable with different notation. So this capital F is my y value, and the change in y with respect to time would be considered the first derivative and little f of t. So I want you to recall, this is extremely important, that we understand that the change in my output, dy, would be equal to the rate of change, dy dt, times the small change in the input. So we have many examples of this. We can take our speed, which is a rate of change of position with respect to time, and multiply it by how much time we spend at that speed. And that would give us how much our position changed, dy. So if we understand this interpretation, we can look at each of these terms here in this expression here as a rate of change times the change in the input delta t. That would allow each one of these terms to represent an incremental change in that capital F expression. So let's be clear on this. F of a would be considered the dy dt value evaluated at a. This is f of a. And we're going to multiply this by the change in time, delta t, right? So I'm just going to write this as one equivalence here. If we multiply that by the change in time, we should get the change in y. And that we understand to be the incremental change in this capital F function, right? And I'll actually call it df, right? as we go from a to a plus delta t. So this represents an incremental change in the capital F function. These terms following will also represent the next incremental change. And notice that at every interval, I am updating the value of dy dt. I am updating the rate of change value because these slopes are changing. So if I go from A to B and accumulate all of these products here, I will be accumulating the net change in my capital F function. This would be the first change in y. I'll call it dy1. And then you add the second change in y over the second interval, dy2, and so forth. And what I'm seeing is that this has to equal the net change in the capital F function, which is not drawn here. We have to imagine that capital F function. But whatever that is, the value of f at B minus the value of f at A would be the net change that's represented by the areas under this f of t curve. Now, all of the principles we spoke about before would still apply in that this is a very rough estimate. As you can see, there's still error. To make this more precise, we would decrease delta t. And we know how to do that. We simply let the number of intervals go to infinity. And that is nothing more than our integral operation. All of the principles that we've spoken about before still apply. The n going to infinity will cause delta t to go to 0. We would rewrite that as a differential that we call dt. And this integral symbol would replace my summation symbol. And the limits, the 2 points on the t-axis where I'm comparing the values of capital F, would now be written on the integral symbol. So now I see an amazing relationship between the area under f of t, little f, and the net change of what we will call the antiderivative, capital F. So this integral here can be found. This integral here with limits a to b can be found by finding the antiderivative, the function that little f is the rate of change for. Finding the antiderivative and evaluating it so that I find the net change between B and A. And we can also find this integral by simply looking at the area underneath the f of t, using any tricks we've learned from geometry. So the area under little f of t could then be used to find net change for an antiderivative for little f. The area under f of t. Now we have made all the relationships that we need to make, including the first derivative of this integral and the area under f of t being equal to the net change in the antiderivative of the integrand little f of t.